Deep learning is a subset of artificial intelligence and machine learning, inspired by the structure and function of the human brain. At its heart, deep learning uses artificial neural networks, computational models composed of layers of interconnected nodes that mimic in a simplified way how biological neurons transmit signals and information. Over decades, the field has evolved, reaching a point where these artificial neural networks are able to process vast amounts of complex data, learning to recognize patterns and extract features that are often too subtle or layered for conventional programming. To grasp what deep learning is, it's helpful to first understand the broader category it belongs to: machine learning. Machine learning is a technique in which computers learn from data instead of relying on explicit instructions. Traditionally, in machine learning, data is fed into algorithms, which then detect patterns and make predictions or decisions based on the input. Deep learning takes this idea further by structuring these algorithms in layers, creating a network that can learn representations of data with multiple levels of abstraction. Imagine teaching a machine to recognize animals in photographs. Traditional machine learning may require a human to explicitly specify what to look for. For example, that cats have pointed ears and dogs have floppy ears, that dog noses are bigger, or that the texture of their fur is different. Deep learning, by contrast, aims to learn these features on its own, directly from raw images, by using multiple hidden layers in an artificial neural network to learn increasingly complex representations. The foundational element of these networks is the artificial neuron, a simplified mathematical model that mimics the function of the biological neuron. Each artificial neuron receives inputs, processes them through a mathematical function, applies a weight to each input, sums them up, passes this result through a so-called activation function, and then produces an output. In deep learning, these artificial neurons are arranged into layers: an input layer, which receives the raw data, multiple hidden layers, which transform the data by learning hierarchical representations, and an output layer, which generates the final prediction or classification. The magic of deep learning refers to the presence of many hidden layers between input and output, sometimes dozens or even hundreds. Each successive layer learns to represent the input data in a new, higher-level way. In the example of image recognition, the earliest layers might detect edges or colors. The next layers might detect shapes or simple objects, such as circles or lines. Deeper layers begin to assemble these shapes into recognizable parts: an eye, a nose, a tail. The deepest layers combine these parts to identify the object as a dog or a cat, sometimes even distinguishing breeds or facial expressions. This architecture allows deep learning models to achieve extraordinary performance on complex problems, especially those with unstructured data, such as world knowledge, sound, images, or natural language. Deep learning models have revolutionized fields like computer vision, natural language processing, speech recognition, and game playing, among others. Training a deep learning model involves presenting it with large amounts of annotated data and adjusting the weights of the connections between neurons through a process known as backpropagation and optimization. Initially, the model's predictions are random or very poor. As the model processes more examples and adjusts its weights, it learns from its mistakes and gradually improves. With enough data and computational power, deep learning models can reach or surpass human-level performance in many tasks. One of the key advantages of deep learning is its capacity for feature learning, the ability to automatically discover the representations needed for detection or classification from raw data without manual feature engineering. In traditional approaches, a domain expert must determine the appropriate features, such as pixel intensities or specific shapes for image recognition. In deep learning, the network automatically extracts and composes these features layer by layer. Deep learning architectures are varied and specialized for different kinds of data and tasks. Convolutional neural networks are designed for grid-like data structures such as images, and excel at capturing spatial hierarchies by applying filters that learn to recognize spatial features and patterns. Recurrent neural networks handle sequential data, such as time series or language, wherein the current prediction depends not only on the current input, but also on past inputs. There are also models designed for unsupervised learning, reinforcement learning, and generative tasks, each making use of the foundational principle of hierarchically structured neural networks. The vast improvements in processing power, especially through the development of powerful graphics processing units and specialized chips, have played a vital role in the advance of deep learning. Modern deep learning models can include millions or even billions of parameters, which require enormous computational resources to train. Similarly, the accumulation of large and varied data sets, from photo libraries to transcribed conversations to scientific measurements, provides the raw material that enables deep learning systems to generalize across wide domains. Despite its achievements, deep learning is not infallible or universally applicable. Training deep networks effectively requires vast amounts of labeled data, which can be costly or impractical to obtain in some fields. Deep learning models are sometimes black boxes, meaning that their internal workings can be difficult to interpret even by their creators. When these models make mistakes, it can be hard to diagnose the cause. Furthermore, deep learning can be sensitive to the quality of the data it is trained on, sometimes inheriting biases or errors hidden in the training set. Nevertheless, deep learning excels in tasks where data is plentiful, and the problem space cannot be easily distilled into explicit rules. For example, in computer vision, deep learning has enabled reliable object recognition, facial recognition, and medical image analysis. In natural language processing, it powers advances in machine translation, automatic summarization, and question-answering systems. In games, deep learning-driven systems have managed to beat human champions at chess, Go, and other complex domains previously considered too vast for brute force computation. To understand how a deep learning model learns to solve tasks, consider the steps involved in a typical training process. First, a dataset is assembled that includes many examples and their correct labels. For instance, when building a visual object recognizer, the dataset might consist of thousands or millions of images, each annotated with the category it belongs to. The images and their labels are divided into subsets: a training set for learning, a validation set for tuning, and a test set for evaluating generalization. The model starts with random or small initial weights. When it receives an input, it calculates an output based on its current configuration. This prediction is then compared to the correct answer, and the difference, called the loss, is calculated. Using mathematical algorithms like gradient descent, the model makes tiny adjustments to its internal weights, moving in a direction that reduces the loss. This process repeats thousands or millions of times, gradually improving the network's ability to make correct predictions. Regularization techniques, such as dropout or weight decay, are often used to avoid overfitting, a situation where the model memorizes the training data but fails to generalize to new inputs. Data augmentation techniques, like rotating images or adding noise, encourage the model to become robust to real-world variations. A crucial development enabling deep learning's resurgence has been advancements in optimization algorithms and the ability to train extremely deep networks. Early artificial neural networks struggled with the problem of vanishing gradients, where information faded as it traveled through many layers, making training very deep architectures impractical. Innovations including new activation functions, normalization layers, and improved optimization methods have largely overcome these limitations, making it possible to build and train networks with hundreds of layers. In application, deep learning has brought about striking practical results. In healthcare, deep learning models can analyze medical images, detect tumors, and predict health outcomes from electronic records with impressive accuracy. In transportation, deep learning powers the perception systems of self-driving cars, allowing them to recognize pedestrians, cyclists, traffic signs, and other vehicles. In entertainment, music and video recommendation engines use deep networks to analyze users' preferences and make personalized suggestions. In scientific research, deep learning assists in analyzing large-scale data from genomics, particle physics, and climate science, uncovering patterns that might remain hidden to human analysts. Deep learning models are now being used to generate data as well as analyze it. Generative models, trained to synthesize new examples from learned patterns, can create images, write poetry, or simulate realistic voices. These generative neural networks learn the structure of the data they are trained on and can produce convincing novel samples, blurring the line between analysis and creativity.